The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon. This is Matt Alexander from the U.S. EPA's Office of Groundwater and Drinking Water. I'd like to welcome everyone to the fourth and final webinar in the Reducing Disinfection Byproducts Through Optimization webinar series. The focus of today's webinar is implementing DBP control strategies, which will introduce control strategy approaches and case studies. All right, so the primary learning objective of this webinar series is to share optimization-based tools and approaches for disinfection byproduct control. These tools and approaches have been developed in partnership with state drinking water programs through the area-wide optimization program. As I previously mentioned, this is the last webinar in a series of 4 webinars. Presentations have been provided by both EPA and state drinking water program staff. Content from each webinar has built on the previous webinar. Supporting information such as study protocols and spreadsheets will be provided and made available through ASWA's website. The intended audience of the webinar series is states and water systems who are challenged with DBP compliance. So all webinars have been at 1:30 p.m. Eastern Time and have taken approximately 2 hours, including a question and answer session. All webinars have been recorded so that they may be viewed at a later date. The recording of today's webinar should be available through ASWA's website in just a couple of days. If you have any questions as we go through today's webinar, please submit them in the questions panel on the right-hand side of your screen. We encourage you not to wait until the end of the webinar to submit questions. Submitting them in advance helps us more efficiently manage the question and answer session. So the first learning objective for webinar 4 is to understand the overall approach to reduce DBPs through optimization. This approach was first introduced in webinar 1, but we have been building on that in each successive webinar. The second learning objective for today's webinar is to understand optimization-based DBP control strategies available to water systems and how they can be implemented. Allison Dugan from US EPA will introduce approaches to evaluate DBP control strategies in the next presentation. Then Jackie Logston from Kentucky Department of Environmental Protection will share a case study where a parent system and its consecutive systems work to reduce DBP levels in their systems. And then finally, William McClymans from Alabama Department of Environmental Management will share approaches that they have taken to manage DBPs and water systems throughout their state. So before I review the information introduced during the first webinar, I'd like to share EPA's disclaimer. The information in this presentation has been reviewed and approved for public dissemination in accordance with the U.S. Environmental Protection Agency. The views expressed in this presentation are those of the authors and do not necessarily represent the views or policies of the agency. Any mention of trade names or commercial products does not constitute EPA endorsement or recommendation for use. So during webinar 1, we introduced a process to reduce DBPs through optimizing existing treatment and distribution system facilities. If you are unable to view the webinar or any of the following webinars, you can access those recordings through ASWA's website. So the overall process consists of 2 stages. The first stage is diagnosing where DBP formation occurs, that is predominantly in the water treatment plant of the parent system and the distribution system, or both. Doing this allows water systems to more effectively prioritize their efforts to reduce DBPs. And the second stage is evaluating and implementing control strategies to reduce DBP formation. So the first step in diagnosing DBP formation is to conduct a diagnostic monitoring study. This consists of collecting DBP samples from the distribution system entry point and maximum residence time locations to determine where the majority of DBP formation is occurring. In addition to the diagnostic monitoring study, an optional initial step is to conduct a distribution system influent hold study. Conducting this study may provide additional information related to disinfectant stability and DBP formation. So during webinars 2 and 3, we introduced approaches to prioritize DBP control strategies in both the treatment plant and the distribution system. The focus of today's webinar is going to be implementing DBP control strategies. So this concludes the introduction portion of the webinar, and now I'm going to turn it over to Allison Dugan, also from US EPA, and she's going to provide a presentation on how to implement DBP optimization control strategies.
Thanks, Matt. Let me pull it up and we'll be good to go. All right. So, as Matt mentioned, I'm going to get into some of the details of evaluating DBP control strategies. If I can forward my slides. There we go. All right. So during this presentation, I'll start with an overview on DBP control strategies and then talk about the process for evaluating control strategies. And just as a reminder, disinfection byproducts form when a disinfectant reacts with natural organic matter in the water. And DBP formation is influenced by several factors, including temperature, water age, disinfectant concentration and type, natural organic matter concentration and composition, as well as pH. Additionally, the presence of bromide in the water can also influence the type of DBPs that form. Of these factors, there's a few things that water system operators can control, and these are the basis for the DBP control strategies that we're going to talk about today. So DBP control strategies are defined as operations-based changes in a water system which lower DBP formation. Some things to consider when implementing a strategy include a strategy may require minor system modifications, which we define as a low-cost change to a system, opposed to, say, an expensive engineering or design change. And often these minor modifications can be done by staff, water system staff. Some strategies can be implemented seasonally, while others may be implemented year-round. It depends on the situation and the strategy. Most systems will have to deal with some type of unintended consequences related to the strategy, which will negatively impact water quality and potentially system operations. And these need to be considered when identifying, prioritizing, and implementing DBP control strategies. And then this may be obvious, but we really want to emphasize that DBP optimization strategies are going to be most effective in systems that have not yet fully optimized to reduce DBPs. And Matt just pointed out that my slides are advancing, but, oh, maybe they all are. Yay. Okay. Let's keep going. All right. So you might recall from our earlier webinars that the potential operations-based changes that can be made in a water plant to reduce DBPs include optimizing oxidation or disinfection, which typically occurs in two general locations, three really. There's the pre-oxidation or pre-chlorination area, and that is what we consider prior to chlorination prior to TOC removal, rather. Sorry about that. Then there's an intermediate location, which is typically like the post-sedimentation basin, top of filter location, and then finally post-disinfection location. And so while we also look at alternative pre-oxidants as part of this strategy, the real impact on DBP reduction is going to come from a system who can lower or stop chlorination in this pre-location. Again, chlorination that happens prior to TOC removal. The second main thing that a system can do is look at lowering finished water TOC through optimized coagulation, and that includes looking at some combination of maybe coagulation dose, the coagulant they're using, and sometimes pH adjustment. And then some water systems have tried to adjust their process pH, which may impact the formation of THMs or HAA5 if the pH is raised or lowered, respectively. But this is kind of a complicated strategy to implement and not one that we're really going to discuss here today. And then there may be other strategies systems can implement as well, but these are the main ones. So prioritizing plant-based optimization efforts was the topic of webinar 2, and as Matt mentioned, if you missed that and you want more information about that, please refer to ASDRA's website for the webinar recording. Also, we've discussed in previous webinars that there are many unintended consequences related to implementing DBP control strategies. And so I want to point out here, we refer to them as unintended because they are secondary or negative impacts of implementing a strategy. However, hopefully with some planning and trying to anticipate them, they can be avoided or minimized, and it'll be less of an issue for a water system as they implement the strategies. And so we've listed all of them here and what two main control strategies they're typically associated with. And we'll go through them more thoroughly during the presentation in the context of evaluating the DBP control strategies on the following slides. And it's important to consider, too, that some of these can be overcome, but others are going to be too difficult for a system to overcome. So that's a consideration as well as you go through the process of evaluating the strategies. Okay. Additionally, there are some resource considerations associated with the treatment strategies, which include costs associated with changing oxidation practices, optimizing coagulants, which again may require an increased chemical dose or an alternate coagulant or chemicals to adjust pH, all of which, or some combination of which, might improve TOC removal. And then there may also be cost considerations related to sludge disposal. Costs associated with bench or pilot scale evaluations of alternate oxidants and coagulants and things like that may also be incurred by the system, as well as costs related to enhanced monitoring, whether it's monitoring equipment or additional reagents or sample analysis, whatever that might be. There's also a resource related to staffing that needs to be considered. It might be skills development and time that they spend with optimization, or there may be other issues as well. And of course, there are other potential considerations which we haven't listed here that may come up for a system. So we're not really going to cover this anymore during this presentation, but we wanted to bring up some of the things that systems must weigh as they move down the path of implementing a DBP control strategy. So shifting over to distribution system control strategies, you might recall this is primarily related to reducing water age in the system, which is generally effective for lowering THMs. Approaches to do this include managing tanks, flushing focused on water quality, and modifying system hydraulics to keep water moving through the system. Sometimes, too, design or treatment changes can be effective, and that might include something like installing a THM aeration system or a tank mixer. And typically, these strategies can be utilized by a parent or a consecutive or purchasing system. So they have a widespread applicability. And prioritizing distribution system optimization efforts was the topic of webinar 3. And so if you missed that one and want more information, please refer to ASJO's website for that recording. As you might expect, there are unintended consequences related to modifying system hydraulics, including tanks. And some examples are listed here and on the following slides. And we're going to refer back to these slides in a little bit. And so we wanted to provide them, and I'll go over these right now, but then they're also a resource if you, after this webinar, go ahead and apply some of this information. So some of the impacts might include reduced capacity for peak demands, such as during times of like firefighting or line breaks, release of poor water quality into the system due to reducing tank levels, low water pressure due to reduced tank levels, release of poor water quality into the system. I'm sorry, we already talked about that one. I'm so excited about that. I wanted to make sure I shared it. But basically, that's going to happen when the tank levels are lowered, and if the tank is not well mixed and the water hasn't, at the top of the tank that's brought into the system hasn't historically been released into the system, it might have a low chlorine residual. So this should be considered and monitored carefully if a system implements a strategy related to changing tank levels. And then some systems have concerns with removing tanks from service. So while that can take out some of the stored volume and potentially some of the water age out in the distribution system, that might be concerning for some. And then additional wear on pumps due to changing tank fill cycles. And then finally, potential hydraulic challenges associated with rerouting water to improve water quality. Customer complaints may also result from implementing DBP control strategies. and some common ones include discolored water, which may result from flushing or changing flow patterns. And this often results from higher velocity flushing or change in flow pattern, but there may be other things too that contribute to that as well. And then customers may also complain if they're in an area where conservation is stressed, and there may be perceptions that flushing to improve water quality is concerning related to water conservation. And then finally, there's other unintended consequences as well, I'm sure, that you should talk with the system if you're working with them to implement a DBP control strategy, and make sure you're mindful of that as you move forward. So finally, here are some examples of resource considerations related to distribution system control strategies. And they include costs associated with installing and operating treatment and/or design changes, such as booster disinfection, tank aeration, tank mixing devices, or flushing devices. Potentially costs related to tank maintenance services, such as inspections, cleaning, recoating, things like that. Costs related to potentially the development and implementation of a unidirectional flushing program. There's also resources, again, related to staffing, which we talked about a couple slides ago on the plant side of things. And then there might be concerns with revenue lost due to unbillable water, such as when a system is implementing flushing to improve water quality. And then other considerations as well, which might be system specific. Okay, so now let's get into the process for evaluating DBP control strategies. And this basically boils down to gathering the data needed to assess the strategy, and then determining whether the strategy applies to the system. And then if you determine that it does, reviewing the potential unintended consequences. And as we discussed, planning for these is really the key thing. And then finally determining whether the system can implement the strategy given the resources needed. So as we move through this, we're going to start with the strategy of evaluating oxidation or disinfection. And in this table, we've split the data that we need into two areas, the pre-oxidation strategy and the intermediate or post-disinfection application. And so the data that we need includes chlorine dose and residual from each disinfection segment in the plant. And the reason we look at this is to simply assess chlorine levels through the plant. And then if the system adds other oxidants, we like to have an understanding of that as well. Sometimes oxidants are added without a clear objective or at a dose that's too low to really be effective. So understanding what kind of dose they're adding and what the treatment objective is for that is really important. And these are almost always added near the head of the plant. So this really is only going to apply if the system's considering the pre-oxidation strategy. Another thing to look at, which is probably obvious, are the inactivation or CT calculations from each segment through the plant. And that applies to both strategies. And then finally, the raw and finished TOC can also be a consideration for this overall oxidation strategy. So there are no real hard and fast rules, but if the TOC in the water is relatively low and the chlorine dose is relatively high compared to the residual, or the chlorine residual that they're maintaining through the plant, this implies that something else in the water is exerting a chlorine demand, which needs to be considered when assessing the strategy. So you might need to also collect data related to inorganic parameters, potentially iron or manganese, to better assess the strategy. So let's start with optimizing oxidation and disinfection and the basis for considering the strategy. So the first thing to consider is whether the strategy even applies to the system. And if the system does not add chlorine prior to achieving TOC removal, they may still be able to optimize their pre-oxidation practices, but it might not have a significant impact on DBP formation. And so for the purposes of this example, though, and working through this, let's assume the system does, and let's assume that that applies. So the next thing to ask is, does or could the system achieve CT through the clear well, opposed to needing pre-disinfection segment to achieve adequate CT? If not, this could really limit the plant's ability to lower or eliminate pre-chlorination. But again, let's assume that they can or they do achieve CT through their clear well and keep moving through. So the next two are somewhat lesser considerations, but assess whether high chlorine residuals are maintained through the plant. And there's probably a treatment objective for this, such as to achieve CT. Or it might be a case of, well, that's what we've always done, in which case you should probe that a little further. And then finally, if total chlorine dose is relatively high to the relative to the TOC concentration, that might suggest some room to lower the dose. But again, you would want to look into why that is. And when you're considering whether this strategy applies to the system, you don't necessarily have to have a yes answer to all of these questions, but obviously the more the better in terms of potential to optimize to reduce DBPs. Okay, so once we determined that the strategy applies, you want to next consider the unintended consequences, which might present major obstacles for the system. And again, our hope is that if we think about these things ahead of time, they won't be concerning issues as the control strategies are implemented. So this first slide of unintended consequences primarily focuses on issues related to CT and in-plant disinfection. So as you're assessing the strategy, look at whether a tracer study has been done to determine the contact time. And if not, and a change in disinfection is going to impact CT and that's being proposed, a tracer study will likely be needed. Similarly, determine whether their clear well is baffled. And if not, that might be needed to achieve CT. And sometimes that's a minor modification for systems and sometimes it's a more major modification, but it's going to be system specific. Another option for systems to consider is to implement a strategy of stopping pre-chlorination seasonally, especially if the system is having a hard time achieving CT in the winter, but can easily do so in the summer. And then, of course, if any treatment change is made to the system, it needs to be approved by the primacy agency. So this is really a bullet intended for the water systems in our audience, in that if you're going through this process, make sure that your state regulatory agency is aware. And so these are the highlights, but there may be others as well. So as you go through and assess this, you want to determine if there's any of these are major obstacles for the system. And if they're not, then you want to continue down the path of this control strategy. So next you want to we want to continue looking at challenges that might arise from the oxidation disinfection control strategy and thinking about oxidation changes at the pre or intermediate oxidation point. So first, considering what treatment objectives they have for adding an oxidant at the pre-location. And some examples are listed here, but there may be others in addition to CT, which we covered on the last slide. So if any of these are concerns for the system and can only be addressed with chlorine, consider whether moving the first point of chlorination downstream and maintaining and could be done while maintaining the desired treatment objective. And of course, doing so might require some additional feed equipment. So that's a consideration as well. On the other hand, if the system is going to stop pre-chlorinating, they'll likely need to evaluate other oxidants. And so this, you need to determine whether this has already been done, and if not, what kinds of studies might be needed before they were to implement this potentially at the full scale. And then there are going to be likely considerations for corrosion control treatment if this change is made in the plant. And there may be other considerations as well, which we haven't listed. So as you consider these, again, if none of these are anticipated to be major obstacles, then you want to continue down the path of implementing the strategy. Now let's look at some unintended consequences that might arise from optimizing the intermediate or post-disinfection location. At this point in the water plant, many treatment objectives related to pre-oxidation have already been addressed. So it's more a matter of making sure CT through the filters and/or clear well isn't compromised, as well as maintaining a plant effluent disinfectant residual that will be positive, will maintain a residual out in the distribution system. The other thing that we really want to emphasize is reducing the disinfectant dose at the intermediate or post location typically is not going to have a measurable or significant impact on DBP formation especially in a free chlorine system that has high water age. So to compromise the amount of chlorine that you're adding at this point for the sake of DBP control is something that a system should very carefully consider because it really may not have a big impact, again, in a system that applies free chlorine and has a distribution system with relatively high water age. So assuming the issues listed on the table, as well as the ones we previously discussed, are not major obstacles and/or can be overcome, and the strategy can be implemented given the resources needed, the system should move forward with implementing the strategy focused on optimizing oxidation in the plant. And it should be done in a stepwise manner, making gradual changes and monitoring, making sure that you continue with the monitoring, not only of the impact on DBPs, but also looking at whether the strategy might be impacting other treatment objectives, including CT. Okay, so that wraps up the strategy of looking at oxidation and disinfection optimization. And now we're going to move over to evaluating optimized coagulation for TOC removal. So the data that's needed for this strategy includes raw and finished water TOC data, coagulant dose and pH data. And as we discussed in webinar 2, it's really good to assess whether finished water TOC tracks the raw water TOC, whether coagulant dose changes with raw water TOC, and what the level of coagulation pH is. You also need TOC performance ratio data, which will indicate whether the system has historically met the TOC removal requirements of the DBP rule by looking at the actual removal or by meeting one of the alternative compliance criterion. And then also, if the system has any recent jar test data, these data might provide additional information about potential for TOC removal. And then finally, any data needed to support potential unintended consequences is also going to be needed. So when considering whether the strategy might apply to the system and whether the system has potential to optimize their coagulation practices for additional TOC removal, review the following. Are there jar test data that suggests the system has potential to achieve additional TOC removal? If so, this strongly suggests that it might be a viable strategy. And if there are no jar test data, could some jar testing potentially be done? We really like to emphasize this strategy because even a small decrease in finished water TOC can result in lower DBP formation, especially when combined with other DBP control strategies. So we know that TOC removal can be challenging for some systems, but it can really have a benefit on DBP reduction for many. So like the example for optimizing oxidation, I'm going to assume that these apply so we can keep moving through them. So now also look at historical TOC performance ratio data and what the actual removal is versus the required removal to determine whether it's less than 1.1 based on a running annual average. So 1 is required for compliance, but in our experience working with systems, we find many can achieve a ratio of at least 1.1 with some simple changes in their coagulation practices, especially if their treated water TOC is still greater than 2 while they're maintaining compliance. So we'll assume that they have this potential. And then similarly, review the monthly TOC, historical TOC removal data to assess whether the actual removal is greater than what was required, even some of the time. And if so, that implies potential for additional TOC removal might exist. And this is the point where you'd want to look more closely at operational data to see whether coagulant dose was modified to achieve this and things like that, which we're going to cover on the next slide. So additional considerations when assessing potential for additional TOC removal include, did the system operate at a relatively constant coagulant dose with little or no consideration to raw water TOC? And so again, this might indicate that additional TOC removal could be achieved at higher doses. Is the system using a coagulant that might not be effective for TOC removal, like maybe more of a polymer? And if so, seek to understand why they are using this coagulant and whether there might be some flexibility to make a change, of course, starting with jar testing to assess that. Is it possible that the process pH could be further optimized for TOC removal? Generally, TOC removal is going to improve as pH decreases, but these benefits can be water and coagulant specific, so definitely something to evaluate through jar testing but for some systems, that's a viable strategy. And then finally, if available, is the majority of raw or treated water SUVA greater than 2? SUVA is a measure of UV254 divided by dissolved organic carbon, and a SUVA value greater than 2 suggests some potential for additional TOC removal. So if these data are available from the system, they should definitely consider that. Okay, so now once we've determined that the strategy applies, we're going to look at potential consequences related to implementing the strategy. So settled and finished water turbidity may increase because for many systems, the optimal coagulant dose for tin shouldn't be taken lightly, this concern. The strategy may also impact corrosion control treatment, and that needs to be considered. And increasing TOC removal, whether you're increasing assuming the issues listed on the slide are not major obstacles and or can be overcome, and the strategy can be implemented giving the resources needed, the system should move forward with implementing the strategy focused on optimizing TOC removal. Of course, this should be done in a stepwise manner, making gradual changes and monitoring not only the impact on TOC removal and DBPs, but also the impact that the strategy might have on other treatment objectives. Okay, finally, let's look at distribution system control strategies, starting with the data that would be needed to assess them relative to the 3 main strategies related to reducing water age, which includes managing tanks, modifying system hydraulics, and flushing. And as you can see, the data that we typically need supports most or all of these strategies. First, if the system has any distribution system chlorine residual data, this may be indicative of areas of poor water quality or high water age in the system. Reviewing this data can provide some insight about areas of the system that might benefit from these strategies. And the chlorine residual sample locations, though, may or may not be near the DBP compliance locations. And so that may be the case that you've got residual data from areas that are away from the stage 2 locations, but sometimes implementing control strategies such as rerouting water or related to tanks can impact a larger area of the system and impact the system much more holistically rather than just at that one stage 2 location. And really that's what we're seeking, is to have overall improvement in water quality in the system. So then we also need information about water storage tanks that the system has, including tank level data and tank characteristics. And so details about this were provided in webinar 3, and this information is used to estimate turnover time and mixing characteristics of the system's tanks using the spreadsheet that we provided in that last webinar. So if you're not familiar with that, I'd encourage you to go back to the last webinar and take a look, and also in the area of ASWA's webinar that provides a link, or ASWA's website rather, sorry, that provides a link to the webinar, you can download the tank spreadsheet and the protocol for using it. Next, we also typically need some kind of distribution map. Ideally, it's going to show location and size of water mains, valve locations, hydrants, tanks, sampling locations, any automatic flushers in the system, and relevant information. That is really helpful when pursuing distribution system optimization. However, we have worked with systems that have a wide variety of maps. Some have all this information and it's current and it's awesome, and others we've started with a street map and marked it up to reflect the most critical locations. And that's awesome too. It takes a little more time, but it's doable. So whatever you use, it's important to have some spatial awareness of the system's water quality and the primary infrastructure that's out in the system and where they're sampling and things like that. And then finally, any data needed to support the evaluation of potential unintended consequences is also helpful, and that might include pressure data or customer complaint information. And if this kind of information can be shown on the map, that's even better. Okay, so we discussed in earlier webinars that distribution system optimization is most likely going to be most effective in systems that meet the following criteria. And again, this is the basis for considering the strategy. So in a system that has plant effluent THMs that are less than around 30 parts per billion, and that suggests that water age rather than treatment is contributing to the elevated DBPs. If you find that the system has not optimized treatment and say the THMs are significantly greater than 30 at the plant effluent location, the distribution strategies can still be implemented, but often both plant and distribution system optimization will be needed to reduce DBPs to a desired level. Similarly, the results from the hold study suggest that the bulk water is not very reactive. And again, these are the samples collected from the bottles throughout the hold study. And similarly, this implies that the plant may already be optimized with respect to DBP control, and that water age in the distribution system may be contributing to low residuals and elevated DBPs. And then finally, the system still has potential to optimize in their distribution system because they've not fully implemented distribution system optimization related to tank operations, flushing programs, system hydraulics, et cetera. And then they would be a good candidate for pursuing distribution system optimization. The unintended consequences associated with distribution system control strategies fall into a few main categories, including customer complaints related to water quality, operational activities, and things like pressure, hydraulic concerns, which might include challenges related to maintaining pressure, issues that might arise from rerouting water, which may also spark some customer complaints. And then, of course, there's our nebulous others category, which systems may have to deal with, and those are going to be system specific. And I presented these earlier on slides 9 through 11, so in the interest of time, I'm not going to relist them. So assuming none of these are major obstacles that the system cannot work around, and that distribution system optimization can be implemented, giving the resources needed, the system should move forward with these types of strategies. And again, it should be done in a stepwise manner, making gradual changes. In other words, don't change all the tank levels at once. And also monitoring in the distribution system should be done not only to assess the impact on DBPs quarterly, but also the impact on other water quality parameters such as disinfectant residual, pH, and temperature, and other parameters of concern, which you'd probably want to monitor on a much more frequent basis than quarterly. So in summary, this process might seem overwhelming, but really it boils down to pulling together the system information related to water quality and operations that you need to assess the strategy, determining whether this strategy would apply to the water system that you're working with, and then considering the potential unintended consequences and resource needs for the strategy. And if the system has the flexibility to implement the strategy, we encourage you to develop an implementation approach that includes careful, stepwise implementation of the strategy and monitoring to understand the impact of the strategy and potential unintended consequences. So with that, I am going to pass this over to Jackie Logston from the state of Kentucky, who is going to talk about a case study with her systems, with a group of her systems.
Hello, my name is Jackie Logston, and I provide drinking water technical assistance with the Kentucky Division of Water Department for Environmental Protection. I'm going to talk about a lot of the same things that Allison was talking about through a case study, and she said at the very end that a lot of this can seem overwhelming, and that's true. Keep in mind as I go through my presentation that this is work that has been occurring over the course of the last 4 years or so. So you're really not going to be addressing everything all at once. Okay, if I can get my slides to advance. Let's see here. I'm not sure.
Jackie, this is Allison. I had a little trouble with it too. I finally ended up hitting one of the arrow buttons. I tried page down, I tried a click of the mouse.
There we go. I got it.
Yep,
okay.
And we got it here too. Thanks.
Right. Thank you, Allison. Okay, so I'm going to talk to you about a system family that's located in the region of Kentucky that I cover. It consists of a parent system with 3 consecutive systems. And so as I go through talking about these systems with you, I'll refer to them as consecutive system A, B, and C. And starting with the parent system, they have an 8 MGD water treatment plant with membrane filtration with an average daily demand of about 2.6 million gallons per day. They have 4 distribution system storage tanks with a combined capacity of 7.5 million gallons. And with this system, and you can see with the combined capacity of the tanks, they've got a lot of oversized lines and a lot of parallel lines. This kind of a good example of they had the money and just build it as big as you can. And now they're really having to deal with the unintended consequences of all that extra water. They provide 100% coverage to the 3 consecutive systems that I'm going to talk about today. They do provide a small portion of water to a 4th consecutive system, but that system gets the majority of their water from another parent system, so I didn't include them in this case study. The parent system serves a system population of about 28,000 with a combined population of about 38,000. The first DBP violation that they received was for TTHMs, and that happened in the 3rd quarter of 2016. And remember that date because I'm going to go back to that here in just a minute. They returned to compliance in the 3rd quarter of 2017. A little background on consecutive system A. They purchase all of their water through one master meter served via a 16-inch line. And truth be told, that 16-inch line acts pretty much like an underground storage tank because there's not a lot of usage on that transmission line serving that master meter. They also have 2 distribution system tanks with a combined capacity of about 600,000 gallons. They serve a small population of about 1,400. Their first violation was for TTHMs, and that happened in the 3rd quarter of 2014. So with the parent system, they got their violation in 16, which was 2 years after the consecutive system was out of compliance. I'll talk more about that in a little bit. They returned to compliance in the 4th quarter of 2017. Consecutive system B, again, purchase all their water through one master meter served via a 10-inch line. They have 3 distribution tanks with a combined capacity of about 500,000 gallons. They serve a population of about 4,700, sorry. Their first TTHM violation was also the 4th quarter of 2014. With these consecutive systems, they all went out of violation at the same time because it happened as soon as they had 4 quarters of stage 2 monitoring data. So as soon as compliance kicked in, they were all out of compliance from the very beginning of that. They also returned to compliance in the 4th quarter of 2017. And then consecutive system C, they purchase all their water through one master meter served by a 12-inch line. They have 4 distribution system tanks with a combined capacity of about 400,000 gallons. They serve a population of 3,700. They've had several violations as well, beginning with the 3rd quarter of 2014 like the others. They also had 2 violations, 2 quarters that they were out of compliance with HAAs, and also returned to compliance like the other consecutive systems by the 4th quarter of 2017. So something that we've done in Kentucky, something that we have implemented is the distribution system optimization training, and we've had a large success using this training. It was a situation where we had a lot of systems that were out of compliance whenever stage 2 kicked in, and a lot of them were the consecutive systems, and we really needed a way to reach all of these systems, as many as we could, as quickly as we could, to start getting this information out to them. So this distribution system optimization training really fit in well. The first one that we conducted was in August of 2015. This is the one that included this system family that I'm talking about today. The training, we open it up. We host them regionally, and now we've had several in different locations across the state. And we invite, in particular, we invite systems that are having compliance issues, but we open it to all systems in the area. When we have a system that is out of compliance, if it's a consecutive system, we also try to get the parent system in the training, whether they're out of compliance or not, because it really helps to get systems working together. In this case, the parent system and all 3 consecutive systems attended the training. And at the time of this training, the parent system was still in compliance, but the consecutive systems were in violation. And something that we were able to do here is when systems are referred to enforcement, they have to submit to us a corrective action plan that tells us what actions they're going to take to return to compliance. And so these systems were able to put attending this training as one of the items in the corrective action plan. The training was well received, but they still needed some additional encouragement to start implementing some of these strategies and to start working together. So after that training, what we did is we pulled the systems together to hold a group meeting, and that was done in mid-October, just after the training was held in August. We had representatives from the parent system and all of the consecutive systems, and the goal really was to get everyone in the same room to encourage communication and collaborative efforts. This really required a holistic approach because, again, we're talking about a parent system that's in compliance, but you've got consecutive systems that are out of compliance. And so it's necessary for systems to work together because the consecutive system really is at the mercy of what's coming to them through the master meter. And at the time, the parent system really did not feel a great responsibility for the consecutive systems violations. They really felt like it was a water age issue past the master meter. So that was where part of the challenge is getting them to see that they still had some optimization potential. And something else that we did is we came up with some action items for each system, some things that they were going to go back to their system and start implementing. And I want to point out too, with the consecutive systems, even though, and you'll see some of the data here in a minute, even though they were receiving water at their master meter that was already out of compliance, instead of saying there's nothing that we can do, it's already out of compliance when we get it, they went ahead and started implementing some of the control strategies that they learned through the training. And because it's a process, it's not something that happens overnight, and really encourage them to do that so that they could start making some progress while their parent system was also making progress, instead of waiting for the numbers at the master meter to decrease before they started implementing anything. And as a result of that first meeting that we had, they have continued to meet annually. It happens in the fall, and they get together, and I can talk more about that later in the presentation. The next thing that we needed to do, and this was a first step for the parent system, was to get the water treatment plant superintendent and the distribution system superintendent working together. And this meeting happened a couple of weeks after the large group meeting. And this was a case, and this is probably common in a lot of areas. They were operating as 2 separate entities. It was almost as if the water plant was wholesaling to their own distribution system. I mean, not literally, but that's essentially how they operated. They There was very little communication. They operated under separate budgets, and they all just did their own thing. And they both were doing a good job. It's just they weren't working together for a common goal. And so through this meeting, they agreed to have regular meetings to start improving the communication, because that really, in this situation, that really was the key to success, to have those water treatment plant operators and distribution system operators working for the same goal. And through this, I saw collaborative efforts between them, and they even did some budget sharing where there was a piece of equipment that the water plant really wanted, and it was expensive, and so the distribution system chipped in a little bit of their money from their budget so that they could buy that equipment, and so they really started working well together. This is the schematic of the water plant, and what I want to point out is this is a retrofit. So it used to be a conventional plant, and then they went in, and this basin here used to be the flocculator and the sedimentation. So they went in and they took out all the guts of this and just left basins. And so there's no arms, there's no mixing, there's nothing. It's just an open basin. I do believe that there's a curtain about halfway to create a little bit of baffling. And then they added the membrane filtration. And the way these membranes work best, according to the manufacturer, is to create a quick pin flock for the top of filter. So there wasn't a whole lot of, there's not a whole lot of time for the whole coagulation, flocculation, sedimentation process to happen. And I'll also point out here on this that they're feeding sodium permanganate as a preoxidant, and then they're post chlorination here after the filters, before the clear well. So things that were not considered that Allison was talking about earlier was moving the point of chlorination, because that was already done. And then there was not a, I'll get in that in just a second. I'll go ahead and move on to this. We did some, to establish a baseline, we conducted a plant profile. And if I'll go back to this for a second, and you can see the different areas, the A, B, C, D, E, F were the sites where I collected the samples to conduct the profile. And the goal here was to try to capture what was happening with each treatment process. And so we started out with a TOC of about a 2.5 milligram per liter. Plant tap TTHMs were about a 43 part per billion, and then the HAAs were 25 part per billion. So that's what we had initially on that. And so our potential control strategies were to improve the TOC removal and optimize pre-oxidation. And we really did most of the work through jar testing to establish if it was an applicable control strategy that they could implement. And again, they were limited on the coagulation process, but also on the types of coagulants that they could use because of the membrane filtration process. We did do some jar testing in that area to determine proper dosage and that sort of thing, but there wasn't a huge change in what they were doing with their coagulant. The preoxidant, like I said, they were already feeding sodium permanganate. They did explore some other options, but decided that the sodium permanganate really was the best. They have some manganese issues at different times during the year, and they find that the permanganate is most effective for that process. So there was some time spent on making sure that they were feeding the sodium permanganate at the right location, feeding it to demand. And then a lot of time was spent on optimizing the carbon feed. And they are limited, again, because of the membrane filtration on the types of carbon that they can feed. In particular, it's called the gold number. A carbon that is too sharp can damage the membrane filters, the fibers. And so they have to be careful there. And so there were several jar tests performed, several trials to identify the best type, the proper feed rate. And something that they played around with a lot was the application point, and that, just as much as any of the rest, impacted the results that they got from their carbon feed. And again, this was a process. This was several months worth of jar testing and trials, but they saw some improvements for sure. Some improvements that made a pretty big impact out in the distribution system because they were changing that reactivity of that water, making it more stable. And so there was a drop from a 2.4 to a 1.7 on the TLC, treated TLC, and then the TTHMs went from a 43 to a 26. I don't have the HA5 data here because this was done in-house, and they have a THM analyzer. I know that type of purchase is not always an option for some of the smaller systems, but that was something that they were able to purchase and have utilized. And so you can see that the work that was done at the water plant, and you know, this was a system that was doing a good job. They were not pre-chlorinating, and they had membrane filters, and you know, they felt like they were doing a really good job, and they were, but it was a situation where they could still make some improvements that would have an impact. And then still talking about the parent system, moving out to the distribution system, they started implementing some of the control strategies that they learned through the distribution system optimization training. One of the first things that we do in that training, and there's a workshop within that training on identifying critical sites, critical locations for increasing the monitoring out in the distribution system. And like Allison said, it really is about the water quality throughout the entire system, not just at those compliance sites. And so critical locations would be dead ends, large oversized mains, parallel lines, low flow areas, tank effluent, areas in the system that you know you have challenges with the chlorine. And the two things that they were monitoring were chlorine and TTHM, because again, they had that in-house THM analyzer, and they can run those tests pretty inexpensively and pretty quickly. So they were able to gather up a lot of data in the distribution system. They also installed a monitoring panel at the main 3 million gallon tank. That tank that I'm referring to, all of the water that serves the whole system and the consecutive systems, all the water goes through that tank first before it's disseminated out into the distribution system. And so it was just a great asset to have that real live data where they could see the chlorine and the pH and the turbidity, conductivity, pressure going in and out of that tank at all times. They're also in the process now of installing more units at other areas in the distribution system because they find this data so valuable. So they increased their monitoring. The next step was looking at optimizing tank operations. So, and Allison touched on this in her presentation, they had to consider, and again, you know, the unintended consequences, but they were looking at how much could we lower tank levels without impeding pressure or fire protection and that sort of thing. They were able to make some tank level adjustments and also change some of the operations with their fill and draw levels to encourage better turnover in their tanks. They cleaned some of their storage tanks, and the biggest improvement that they made was to that main tank that I talked about on the last slide. They recoated the interior. It had been a long time since the tank had been taken down and cleaned. There was some corrosion issues in the tank. There was stagnation issues in the tank. So they recoated the interior and they installed a mixing system. And I want to make sure and tell you here that mixers improve the mixing, but not the water age. So you still have to have some movement in and out of that tank to keep the water fresh. If you're mixing old water, it's still old water. But a mixing system can be beneficial in a situation like this one for sure. Again, this system had what they considered a good flushing program. The entire system was being flushed 2 times a year, but it was not they had some improvements that they could make to it. And so they do try to do some unidirectional flushing where they can. That's not always possible, but conventional flushing along with that. They do that twice a year. They also do some low velocity flushing. We call it soft flushing in critical areas quarterly. This is in areas where they were having some chlorine issues, or again, using that THM analyzer, they knew that they had some areas. And again, they're looking at the whole system. They're not just looking at their compliance sites, but where in the system do they see the THMs increasing, and using that to do some turnover flushing where they're doing the cleaning, the scouring twice a year, but more on a more regular basis, they're turning that water over because they have so much storage, because they have so many large lines, and keeping that water turned over. They also systematically installed automatic flushing devices, and again use that THM analyzer to determine the best locations. And then something else, and this was something that came out of that first meeting, was coordinated flushing efforts with their consecutive systems. And so they would let the consecutive systems know when they were going to be flushing, so that the consecutive systems could piggyback off of their flushing, so that when they started flushing from their master meter, they were pulling through that freshly flushed water from their parent system. They also did some valving manipulation to eliminate some hydraulic dead ends and get water flowing in different directions. And they're working on a plan to eliminate some of the parallel lines. So they are trying to address that in some manner, but that's a difficult fix. That can be expensive because they may have two lines running together, a situation where it was a small line, they needed more capacity, and instead of upgrading the line, they laid another one next to it and having customers tapped into each of them. So that's going to be a long process for them, but it is something that they're addressing. And then something else that they did, and this is different, this is separate from what came out of the optimization training, but one of the things that they started doing at this system was they began feeding a biopenetrant, and this was to address any biofilm issues that they may have out in their distribution system. And they monitored the effectiveness of it by chlorine residual monitoring. This chart here is looking at the long-term trend of the trihalomethanes. It is taking the maximum LRAA from each quarter and doing an average of the max LRAA. And the solid line is the long-term goals. So we set a goal of 60 for all of their sites, figuring in the max. And the average is the dotted line, and you can see that they're falling below that long-term goal. So this is the parent system, and of course the 80 is the MCL, but this system went from being out of compliance to now meeting optimization goals. So that's quite a success that they have demonstrated there with the control strategies that they implemented. I'm going to move on now to consecutive system A, and like Matt was talking about in the introductory, starting with diagnostic monitoring. So we did some diagnostic monitoring of the distribution system. We profiled essentially their distribution system. You can see that the master meter was already out of compliance with TTHMs, so they're receiving it out of compliance. You know, some systems may throw up their hands and say there's nothing that we can do about that, but that was not the case with these consecutive systems. You can see the chlorine residual dropping. As the chlorine goes down, the TTHMs go up. The HAAs actually go down. They're probably looking at a biofilm issue. That was not something that was evaluated in this system. There is a tank influent and a tank effluent. They have two tanks, this system does. We just included one of the tanks in the profile, and that tank had a separate inlet outlet, but it was a unique setup because that tank was used for fire protection for an industry, And so the effluent was actually a riser pipe in that tank that would keep it from falling below a certain level. And so the water would become stagnated, but there were several feet of water at the bottom that could not get out because of that riser to maintain a minimum level in that tank. So that was one of the challenges that they were looking at there. And we also did look at tank spreadsheet and water age. We weren't able to use it on this one because of the piping configuration, but we were able to use it on their second tank. So they started implementing control strategies they learned from the distribution system optimization training. And again, when you're looking at the distribution system, Allison said that well, you're really looking at reducing water age. So they looked at optimizing tank operations. And so what could they do to increase the turnover but still maintain adequate fire protection? And so those were the things that they had to evaluate when changing tank operations. They really ran into some hydraulic challenges in this system because they were operating off the parent system pressure. And then the two tanks that they have do not operate on the same elevation, and there was a different elevation from the parent system. And then again, I talked about the tank that was used for fire protection with that riser pipe in there. So they did go into that tank in particular, and they removed that riser pipe, and so they didn't have that issue anymore. They also recoated the interior of the tank because there were some corrosion issues, and they installed the same duckbill valve mixing system in that tank. And then optimization efforts for their flushing program include a system-wide conventional flushing. They aim for twice a year on that. They do some low velocity soft flushing in critical areas quarterly, again looking at the whole system, not just your compliance site areas. They were able to install a limited number of automatic flushing devices, and again coordinated flushing with the parent system. And then this is their long-term trend. So as you can see, and this only goes back to 2017, but that at that time they were above 100 on their max site. And so they have really seen some significant improvements in their long-term trend at that system. I'll move on now to consecutive system B. Again, we conducted some diagnostic monitoring of that system, and one of the sites that they were really challenged at, their two compliance sites, would be the SM2 and the SM4. Coming in at the master meter, it was not as high as it was for consecutive system A, but this system was located a lot closer to the water plant, and it also had a smaller, I forgot to mention that as I was talking about consecutive system A, the impact that 16-inch line had on those master meter results. They were really high. But this one, a smaller line serving it and not as far from the water plant, so that helped them. But you can see that the SM4 is located out in the furthest part of the system there, and greater than 100 on that. But you can see the drops in the chlorine residual as those TTHMs increased in the system. Something else they did here is they did some BARTS monitoring, which is the biological activity reaction test. And they found some iron-reducing bacteria presence at some of the locations in their system. And you can see by the brown color, brown is a presence. This one had some brown in this one. So they did find some iron-reducing bacteria. And as a result of that, they made the decision to install the biopenetrant feed as well. And that went in just downstream from the master meter. And along with that, they put in a phosphate feed. The parent system does feed a phosphate, but they added a little extra just to give it a little boost from that level measured at the master meter there. And similar flushing program with this system. They try to do a system-wide conventional flush twice a year. They also do some low velocity flushing to turn over those long, because we're talking about a rural area. I didn't mention that earlier. These consecutive systems are rural areas in Kentucky. So you're looking at long, low customer, low number of customers on long lines that go way out. And so keeping those lines turned over is essential in keeping good chlorine residual and keeping the water age down. And then also coordinated flushing with the parent system. And then with their tanks, they made some adjustments where they could to the fill and draw levels to increase the turnover. And they did, believe they did lower some levels in some of their tanks to reduce the amount of water that was in storage. They also had the duckbill valve systems installed in all of their tanks and cleaned all of their tanks as well. And then here's their long-term trend. And so they're doing really well as well. They started out, and again, this only goes back to 17, and they've been out of they were out of compliance beginning with the third quarter of 14. But you can see, or 15, 14, anyway. But you can see the improvements that they've made over time with their results there. And then moving on to consecutive system C, we didn't do the extensive diagnostic monitoring at this system as we did at the other two, but we do have some additional monitoring that was done at the master meter and the two monitoring sites, and you can see that it was coming in at over 100. So they had some challenges there at the beginning, pretty high levels coming in that needed to be addressed. And you can see too on this one that the SM3 site, the HAAs fall off there too. And again, that may have been a biofilm issue. We didn't identify that though, but implemented control strategies that they learned in the training as well. And a challenge that this system had was they have a limited number of flush points. They don't have that many fire hydrants. It's not a fire rated system. Again, we're talking, a rural area, but they just don't have very many flush hydrants either. So they do the best that they can flushing, but that is a big challenge still to this day, and that's something that's going to come with time and money, is to install more flush hydrants so that they can turn the system over better. And then with their tank operations, they did make some adjustments to the fill and draw levels to increase turnover and lowered some tank levels in areas where they could without having a negative impact on pressure. And then here is their long-term trend. And so you can see that those numbers have trended down below compliance for several quarters. So really what we learned through all of this is that the success that these systems achieved really required a holistic approach. Without the parent system being willing, and they started their work before they were out of compliance, but it really took them being aware of the system as a whole, not just their little kingdom, but the system as a whole, and everyone working together. All of the systems have maintained compliance since the third and fourth quarters of 2017, and some of them are even achieving optimization goals. So we consider that a great success. Like I said earlier, they've continued meeting on an annual basis. They get together for lunch and they talk about compliance. Sometimes I'll go and give a little presentation on what everybody's numbers look like. They talk about coordinated efforts, any projects that any of them have going on, sampling with the THM analyzer that the parent system owns. They do sampling for their consecutive systems if they want them to do that. And I think that this is just really a great example of the benefit gained by communicating and working together. And with that, we'll turn it over to William in Alabama.
Thank you, Jackie. As Jackie said, my name is William McClymans. I'm in the not surface source section. I'm still getting used to the change. I'm in the water supply engineering section of the drinking water branch in the Alabama Department of Environmental Management. Okay, apparently I'm having the same problem. There we go. Today we're going to talk about, this will give you a breakdown of Alabama's drinking water information. We're going to go back in time a little bit to talk about the Stage 1 disinfection byproduct rule, some of the predictions we made back then for our future Stage 2 compliance, our finished water TOC goal, which we've adopted in the state, talk about our master meter monitoring, then we're going to talk about OELs, which is your operation evaluation levels, the distribution system evaluations, and we're going to talk at the end some about the area-wide optimization program. So some basic information about Alabama. We currently have 510 community water systems, which is comprised of 77 surface water systems with 98 surface water treatment plants amongst them, 244 groundwater systems, 150 purchase systems, and 39 groundwater purchase systems. We currently have approximately 240 systems on quarterly DBP monitoring. Other things that also has been beneficial but also a hindrance in the state is we have a high level of interconnection between our water systems. And one of the biggest things that we also have going on in our state is all of our community water systems are on free chlorine. So back in Stage 1, the way we originally set up Stage 1 was the parent system was responsible for everywhere the water went in the beginning. This is back in the early 2000s. So they were actually monitoring the water in the consecutive systems to determine compliance with Stage 1. And that caused some problems with, I'll get that in just a minute. And so with that and the future of Stage 2 looming on us, we decided to make some changes to to our Stage 1 regulations. And what we required starting in 2006 was we knew we had problems in our distribution systems, but we weren't really sure, how much our water treatment plants were contributing to that problem. So in 2006, all of our surface systems had to start monitoring the effluent of their water treatment plant every quarter when they did their Stage 2 monitoring. And I'll show you some examples of that in just a minute. Also in 2006, we altered to where the consecutive systems had to do their own Stage 1 monitoring. So beginning in 2006, all the consecutive systems that never had to do any disinfection byproduct monitoring all of a sudden had to start monitoring. And then in 2007, the parent systems were able to pull their monitoring back within their own systems. And a lot of the reasons for this was complaints, and we had complaints between water plant operators and their distribution operators of, who was responsible for what, and that's where the water plant effluent monitoring came from. We also had fights between parent systems and consecutive systems as well. So on the water treatment plant effluent side, what you have here is two different water treatment plants, and it goes from first quarter 2006 through fourth quarter 2008 in each of the examples. And you can see, I threw up an example of where one water plant had a TTHM problem where, it's putting out really high TTHMs, and the scales on both charts go from 0 to 80 if you are unable to read them. And you can see a lot of the results, leaving the water plant are above 40, and one of them was above 70. Then similar on the other plant, had a halo problem, with some of its results up near 80. So when we started this water plant effluent monitoring, it really started showing us, where our problems were. Some water plants like these, had to take note and realize that, that they were the problem. And, some of the water plants realized that they were only part of the problem, and then some water plants actually got vindication because they already had good numbers leaving their water treatment plant. So on the next slide here, we actually have to show you some of the improvements our water treatment plants have made. We got the same water treatment plant from the previous slide that had a halo problem. So the top chart is their 2006 to 8 data, and then the bottom chart is their 2016 to 2018 data. And you can see this water treatment plant has made vast improvements in controlling the TTHM and the halicylate acids leaving the water treatment plant, and pretty much, have met some of the goals we have for the water treatment plant effluent, which we'll talk about later in the presentation. Another reason for changing our stage 1 was, we were looking at stage 2 and what the stage 2 rule was going to cause, and our, how much problems we were going to have, going from a system-wide running annual average to where each individual site, was going to stand by itself. And this is the oldest data I could find that I could actually put my hands on. I've got some older predictions, but I couldn't able to find them. But in 2006 and fourth quarter, using that stage 1 data, using and comparing it against, the stage 2 calculations, we were predicting, that 60 systems would be in violation of stage 2 if nothing changed. And 100 of that 130 sites, would be above the limit. And then you can also see results there for first quarter 2007 and second quarter 2007 as well. And we went farther back in time, just looking at the parent systems, some of those numbers were even worse. And I'm saying this doesn't even include the halicylate acid information. This is just the TTHM non-compliance estimates from 2006. The other thing that bothered us, was the operation evaluation levels. And here's, from third quarter 2006 to fourth quarter 2009, just the number of sites that would be triggering operation evaluation levels, if stage 2 was in effect back then. I mean, you can see, the numbers are astronomical. We would have been doing, OELs all the time in the state, and that really concerned our supervisors, about how much work this was going to put on the staff to be able to keep up with these and also help the water systems, deal with all these problems. So, and then one of the other things we did during this time was we also started, looking at our water treatment plants, not only from, the effluent DBPs, but, we also started looking at their TOC removal. And what we found was that the performance ratio is not a good indicator of optimized TOC removal for DBP control. Some things we saw, some of our plants that had greater than 50% removal of TOC, still had, DBP issues in the treatment plant and in the distribution systems. And the other thing we saw was systems with a finished water TOC less than 2 milligrams per liter tended to have lower DBPs in the treatment plant and in the distribution system. So noticing this, we went back, we analyzed, our water plant TOC and effluent DBP data, and we found that if our water plants could get to at least 1.7, it tended to lower the disinfection byproducts leaving our water treatment plants. And also, by doing that, it also gave the distribution systems an increased chance of maintaining compliance. But we also acknowledge, in some of our systems that even 1.7 is not low enough. One of the water systems I currently oversee, their actual target is 1.2. Of course, their raw water is below 2 to start off with. So, but they have to get down to a 1.2 to be able to maintain, the water treatment plant effluent at good numbers to help maintain their distribution system. Some of the other things we've noted is, since we've been doing this, we started generating spreadsheets that assist us with different aspects of our program. And this is just a couple of the charts off of one of them. And we're talking about this during inspections. And then one of the things we started noticing is, when we start seeing spikes in the TOC, a lot of times we're also noticing it during the DBP. So we're able to take this out during inspections, start showing operators like, this happened, look what it did to your disinfection byproducts. So, they're able to begin to realize what was really going on and they started taking note of some of this information. With that, kept going on. We still had a lot of issues between parent consecutive systems, you know, and they were fighting over water quality. And some, like I say, some of them have been fighting since 2006, you know, some even longer, going back to, you know, early to the 2000s, back when the parent systems were responsible for the monitoring, because the parent systems back then say, you know, we can't force the consecutive systems to flush, you know, they're causing all our problems, you know, and that, you know, caused us, you know, to put the consecutive systems on their own monitoring. You know, of course, then in 2006, you know, the consecutive systems, you know, were complaining, you know, about the water coming across the master meter, that it wasn't good enough, you know, for them to be able to comply, you know. So, you know, and this went on for several years, and then, you know, as stage 2 approached, you know, the complaints just were getting worse and worse from the parent consecutive systems, you know, and so during one of our annual meetings, our branch chief stood up, you know, and told the systems to work it out, or ADEM would work it out for them. And that's where the master meter monitoring came from. It's because the systems, you know, were still, you know, not getting the water improvement that we needed. So in third quarter of 2012, you know, we implemented master meter monitoring, where the parent system was responsible for, you know, monitoring at every point where they sold water to a consecutive system. You know, we just told them it was part of them doing business. We did exempt groundwater systems, you know, unless an issue arose, because most of them had low or non-existent DBP. So, you know, we went ahead and, you know, exempted them, you know, unless an issue came up where we needed to, you know, have them start master meter monitoring. The other thing is, even though the parent system is doing the monitoring, the regulation also requires them to provide the results to the consecutive systems, you know, so the consecutive systems are getting that information. And we also, in the regulation, allow for reduced monitoring if systems could show, you know, that the master meters, you know, were not causing a problem for their consecutive systems. Here you got 2 results from our master meter monitoring results. The one on your left is, well, the master meter is out of control. And currently the parent system is in violation because one of their compliance sites is this master meter. So they've been in violation for, I think, 2 or 3 quarters now. And, you know, they're now having to deal with this issue. Then the one on the right is, you know, a master meter that's actually in pretty good shape. You know, so, I mean, when we implemented the master meter monitoring, we started getting a lot of valuable information out of them. You know, and some systems have taken the information and ran with it, while other systems, like the one on the left, you know, just basically, you know, we're trying to push it off and not have issues, you know, and just saying, you know, well, it's the consecutive system's responsibility. Some of the other things we've done in the state is, you know, we talk about the operation evaluation, you know, what kind of problems we were going to have with it is, you know, we also, which each state had to do, was develop, you know, a report, or, you know, what the systems were going to do when they had an OEL exceedance. So we designed our report. It does a good job of determining why the source of water treatment plant is the culprit and why it occurred. So it does a really good job in the plant and the source, but it doesn't do very well in the distribution system. Mainly that's because of the lack of information in the distribution system. As there's so many things going on in the distribution system that can lead to the high disinfection byproducts. The other thing it was designed to make the operators not to ever want to fill it out again. So, you know, a parent system, to fill it out completely, it's 23 pages, and a purchase system is 9 pages. You know, so we wanted to get the information that we needed to be able to, you know, to figure out what was going on. But, you know, basically it was also designed, you know, hopefully to lead the operators to, man, I've got to fill out another one of those reports. I don't want to do that again. So let's see what we can do to lower our disinfection byproduct numbers. The other things we've done also in 2012 is we instituted the joint OEL and mandatory meeting. And what this does is if a consecutive system exceeds the THM or the HA5 MCL, then the parent and consecutive systems have to do some things. First of all, they have to fill out what we call a joint OEL. It's basically all the systems involved throughout, from where the water is produced at the water treatment plant all the way through the consecutive system that had the violation, all have to be a part and fill out, an operation evaluation level report. And then they also have to turn those into the state. And then after that, all the systems involved have to sit down at a mandatory quarterly meeting to discuss the OEL and the measures that can either be taken to reduce the disinfection byproducts, or, if it's an ongoing violation, how are the current actions that they've taken to correct the violation, of helping, what needs to be done in the future. And then also one of the other things to make sure that these occur is they have to submit an attendance list and the meeting minutes to the department within 30 days of the meeting. The other thing that we've done in the state to help with stage 2 compliance, which a lot of you probably won't think that it's helping, but we don't have an initial distribution system evaluation in this state. We just do distribution system evaluations. This was from the get-go. This was already planned. Our regulations require our water systems to do a DSE every 9 years unless one of the following conditions is met: the addition of a new surface plant, new groundwater source not in the same aquifer as other sources, new purchase connection, system consolidation, or we have a caveat in there as required by the department. The second DSE actually started in 2016, and our Schedule 4 system reports are due by July 1 of this year. So we're in the process right now of finishing up our second distribution system evaluation. Some of the things that came out of that is most systems moved at least one of their max sites. Several systems had all new sites, and some of the results from the new sites were 20 to 80% higher than the previous year. So, we moved sites and the numbers went up. And what that's forcing our systems to do is they got to fix their entire distribution system instead of just fixing one location. They're now realizing, they've got to take a holistic approach to their distribution system, because in a couple of years, starting in 2024, if they don't fix their distribution system, well, they're going to end up with new monitoring sites once again, and they'll have to start all over with, trying to correct their distribution system. And a lot of the stuff that we've done is also came from our area water optimization program that we participate here in Alabama. Some information about that: Alabama joined the Region 4 AWOP in 1997. The initial focus back then was on turbidity removal, because that was the big thing back then after the Milwaukee incident. And, it was all about turbidity, but then disinfection byproducts were really becoming an issue. So we expanded the scope in 2004 to include DBPs. What we did to do that was we added a session to our microbial or turbidity-based, performance-based training. What I say was to address water treatment plant DBPs, and we focused primarily on TOC removal using UV 254. We talked about THM Plus and used it some to help diagnose initial problems in our treatment plants. We don't actually use THM Plus in the state anymore due to issues and sensitivities of the results, and there was very little distribution work at that time, because mainly we were focusing on the water treatment plants. And this was even before we implemented water plant effluent monitoring. Then in 2006, we started expanding to the distribution systems. It was limited. We started talking about the storage tank spreadsheet. We started looking at turnover time in storage tanks and their mixing. Then in 2011 is when we really started working with our distribution systems with the Coleman project. We adopted distribution goals, which we'll go over here in a minute. We also started to develop a ranking system to help prioritize our water systems. And currently, we're so into our performance-based training, we're currently conducting our 7th series and getting ready to start an 8th series of this distribution performance-based training in the next couple of months. Our goals for our distribution system There's actually a lot on this page if you look at it though, but I wanted them all on one page so you can kind of see where we're at. We have our distribution DBP goals, which, are basically for THMs and halos are to be 10 parts below the MCL. We also have long-term goals looking at the maximum sites during any quarter for disinfection byproducts, and over a 11-quarter time span, almost 3 years worth of data. What we want to do is we want to see those be less than 60 parts per billion for TTHMs and 40 parts per billion for halosic acids. And back when we adopted these goals, EPA did some analysis and basically determined that if you could get your numbers down to these points, you had a 95% confidence rate of maintaining compliance. Like I said, we also adopted water plant effluent goals. So, what's entering the distribution system, we want our water plants to be below 20 parts per billion for halosic acids, 20 parts per billion for total trimethanes, 15 parts for halosic acids. We also want the TOC entering the distribution system to be 1.7 or less, and also to maintain, the water plants also to maintain the contact time to be able to make sure that the water is properly disinfected before entering the distribution system. For chlorine, it's slightly different than our reg. Our regulation requires a 0.2 milligram of free chlorine everywhere, and here we have a 0.20. Minor difference, but sometimes, it can make a huge change on the way the operators operate their distribution system. Storage tanks, we want the turnover time to be less than 4 days, and we want the mixing ratio to be greater than 1, so we don't want the storage tanks turning over and mixing. Distribution pH, something that a lot of people may not realize is one of the things we found through the years is the pH, especially in our low alkalinity surface waters, is changing in the distribution system. Some severe cases have gone from about 7.2, leaving the water treatment plants, to 9s and 10s in the distribution system. So we've got a pH goal for our distribution system is basically we want to be within 0.3 pH units from the water entering the distribution system, either from the water treatment plant or their master meter. And some of the more recent things we found is temperature. Basically, when it comes to temperature, we're looking for the temperature to be consistent throughout the distribution system. Should be less than 5 degrees Celsius, preferably less. Difference, anywhere you measure the temperature in the distribution system. And if you were on the last presentation, I talked about thermal stratification, and systems, seeing elevated temperatures in their distribution system. So, we want the temperature to be consistent, throughout the distribution system. And to help us with our work, we've developed spreadsheets over time to help us, where are we going to, be doing our work. And this is just a snapshot of two of those spreadsheets. On the top one is basically it goes in and looks at each of the 240 systems that's on quarterly monitoring. And this is just a small segment of that spreadsheet. You don't get to see everything there, but it goes in and does a bunch of calculations, and it assigns a point score for those systems. And then based upon that point score, it can be sorted, and then, so the systems that have the higher points, are in the worst shape, and those are the ones that we target generally for, assistance through our area-wide optimization program. Then the chart on the bottom just shows from second quarter 2017 through the first quarter 2019, how we're doing as a state. As of first quarter 2019, we have 184 out of 240 water systems, that are meeting our disinfection byproduct goals in the distribution system. And then the other lines on there just as a breakdown show you, how we're doing in each of the different categories that it looks at. So in Alabama, we've achieved increased compliance by being aware of the problem. We have our quarterly status component that we can sit there and look at and see how we're doing. It takes about 20 minutes to run due to automation. Basically, I've got to the point where I sit there and enter 2 dates, the start date, the end date, and then hit the update button and come back 20 minutes later and it's done, then I start looking and making sure, you know, are we missing data, you know, things like that, you know, and then fill out the blanks, you know, and then rerun it if necessary. Like I say, and it prioritizes systems based upon the disinfection byproduct level. So it gives us, you know, an idea of which systems, you know, needed systems, you know, and we start going through that list every time we get ready to start, you know, something new in our optimization program. We use that list to go through it to help us figure out where we need, in the state we need to do our work. Other increased compliance is by taking a proactive approach at the state level. Like I say, in 2006, we implemented the water plant effluent monitoring. In 2012, we introduced a master meter monitoring, the joint OELs. Then also during our inspections, both annual and sanitary, you know, we talk about performance with our systems as well. We not only talk about the turbidity performance, but we also talk about, you know, their disinfection byproduct performance, you know, and if we're in the surface treatment plant, you know, we also talk about, you know, how the treatment plant itself is doing with the water plant effluent and the TOC as well. Also by educating the operators, we found to be highly beneficial. In Alabama, we hold an annual surface water meeting. We've been doing it for 22 years. So, you know, presentations at that meeting cover regulations. It covers, you know, any topic, you know, was deemed relevant, you know, for our surface water systems, including optimization activities and, you know, what other systems have done to, you know, to assist them in, you know, improving their performance. We also have presentations at the Alabama Rural Water Association and the Alabama Water and Pollution Control Association's annual conferences. We held other classes, you know, with different organizations throughout the year. A lot of the spreadsheets that we develop, we also hand out to our water systems, you know, so they have access to all of our spreadsheets as well. And then performance-based training is one of the biggest benefits we've seen is, you know, because when we do distribution performance-based training, you know, we target the parent and the consecutive systems, you know, so if a consecutive system is having issues or the parent system is having issues, you know, we look at that and we boil in, you know, all the systems for that parent system, you know, so we go and try to target, you know, one area and try to pull them all in together and try to, you know, get them to start, you know, working together, similar to what Jackie was talking about. It teaches operators to diagnose the problems, you know, so the operators begin to learn, you know, how their distribution system actually functions and works, and they get a better understanding about what's going on in their distribution system. And the other thing is it also teaches the state staff how to help with issues as well, because as the state staff is going through these training classes, you know, they're learning as well, able to help, you know, not only the systems going through the training class, but, you know, there are other systems that they oversee as well. So in summary, best thing I can tell you is be a part of your EPA's regional area-wide optimization program. Develop a way to track your water systems and your water treatment plants, and be proactive, not reactive. And with that, I'll turn it back over to Allison or Matt.
All right, so we'd like to thank Jackie Loxton from Kentucky and William from Alabama for contributing to today's webinar. And we'd also like to thank all the presenters from the previous webinars that contributed to this webinar series. And lastly, we'd like to thank ADSWA for giving us the opportunity to participate in this webinar series as well. So before we start the question and answer portion of the webinar, I'd like to quickly review today's learning objectives. The first objective we had was to understand the relevance of this webinar series and the DBP control strategies that we shared. I know that many states and water systems are challenged with DBP formation, so I hope that this webinar series was relevant. Our second objective was to understand optimization-based DBP control strategies available to water systems and how they may be implemented. So Allison shared an approach to implement control strategies in the second presentation, and then Jackie shared a case study where a parent system and its consecutive systems work to reduce DBP levels in their systems. And then William just shared approaches that Alabama has taken to manage DBPs in water systems throughout the state. So thanks again to all of our presenters. And now I'd like to begin the question and answer portion of the webinar. I'd like to thank everyone who has submitted their questions in advance. It does help us more efficiently go through the question process. So To get started, I think I'll direct the first question maybe to Jackie, if Jackie's ready. The first question for you, Jackie, was what type of coagulant did the parent system use in your presentation?
They use an ACH, aluminum chlorohydrate, for coagulant.
All right, well, thank you. And now we'll direct the question to William. We'll try to spread these out, presenters, just to make it a little easier. William, we got a question from Maureen Pepper. She wants to know, for master meter monitoring, what was included and where were the samples taken?
The master meter monitoring is just like any other DBP monitoring that the parent system has to do. So they had to monitor for disinfection bioproducts, both the THM and the halocic acids, and it was at every master meter where they sold water to another water system. So some systems, picked up, 20 sites for their master meters if they had a lot of master meters with their consecutive systems. So, yeah, it's disinfection byproducts at all the sites where they were selling water.
All right. Well, thanks, William. The next question I'll answer, and it's from Alan Tyler. Alan asked, have there been any case studies which evaluate the pros and cons of flushing versus installation of mixing and aeration prior to setting on a course of action for optimization? So in my opinion, Alan, those are kind of two different things. Flushing is going to reduce water age out in the distribution system. Aeration and mixing is only going to help you if you find that tank is currently not well mixed, or there are a lot of THMs accumulating in the plant in that tank. So I would start by doing some investigative sampling out in the distribution system first to try to see if there's any areas of high water age that you find, and then from there you might consider implementing some type of a flushing program to reduce water age. With the storage tank, if you look back at some of the information we shared at the last webinar, webinar 3, we talked about storage tanks and some studies that could be conducted to assess if there's high water age in the tank. There was a tank spreadsheet that we introduced. Also doing some in-tank monitoring. There are some case studies that Paul Hankey from the state of Pennsylvania provided to assess storage tanks. So if you find out the storage tank isn't well mixed or you're forming a lot of THMs in the tank, that might suggest that a mixing system or aeration system might be a viable option. All right, the next question, I believe we'll give one to Allison. Allison, this question is from Joe Crisolago. He asked, placing baffles in the reservoir can increase CT. This may help reduce pre-chlorination.
Yep, thanks for the question, Joe. So, and I may not have been clear in the presentation, but I was suggesting that baffles would be placed in a clear well at the water treatment plant in order to increase the contact time or the amount of time that water spends in the clear well, which a system would probably be relying on to get disinfection credit. And so for some systems that can maybe be a relatively minor change to put those baffles in. For others, it might be a more significant cost. But if the system is in a situation where they don't get a lot of contact time in their clear well, and they can install that, then they can maybe decrease the amount of chlorine they're adding further up in the plant, like maybe in the pre-chlorination location, in exchange for getting additional CT in the clear well, in the newly baffled clear well. I wasn't suggesting putting baffles in a reservoir out in the distribution system, in case that wasn't clear.
All right, well, thanks, Allison. The next question I'm going to direct towards Jackie, and I'm going to try to summarize. You've received a few questions related to this. Could you please tell more about the biopenetrant that was used and maybe give some examples of some chemicals that are considered biopenetrants?
Okay, so this one in particular goes by the brand name of Claritas. I've also seen systems used one by the brand name of Oracle. But the biopenetrant, the way it's been explained to me, the way that it operates is it penetrates the protective coating over the biofilm, which then allows the chlorine to get in and disinfect or kill the bacteria that's in the biofilm. It is NSF approved. I did see that on part of the question. And they feed it, they start out slowly and increase the feed, start out maybe around 5 parts and maybe get up to around 15 or 20 parts. So it's not a high feed rate. It's much, much lower than the NSF maximum use certified level. And the effectiveness is measured by chlorine residual. And what I mean by that is like if you see low chlorine residuals or if you see a large gap between total and free chlorine, what you'll start to see over time as that biofilm cleans up is the numbers, the total and free numbers will not have as large of a gap, and then just the sustainability of the chlorine residuals increases, higher chlorine levels that don't fall off as quickly, like in areas that have to be flushed on a daily basis or every other daily basis to maintain that chlorine residual. Their operators are seeing that they're able to go a longer length of time before they have to clear that line to bring the chlorine residual up. So I hope that answers the question. If anybody has any needs some more detail than that, feel free to give me a call or email me, and I'll be happy to answer it in more detail.
All right, thanks, Jackie. And likewise, I got a question for William McClymans, and I'm going to try to summarize. You received a few questions about this that's related. So kind of in general, under what authority does Alabama use to require joint OEL and mandatory meetings? And how do they enforce it if systems fail to submit attendance lists to the department?
Well, the second part of the question is easy. We've never actually had anybody that failed to turn it in, that to my knowledge. So we've never actually had that come up. But the first part of the question, it's actually in our regulations. So, you know, it's written in our regulations of the state. We're not restricted like some other states are to only being as strict as the federal rules. So, you know, we put it in there and, you know, it got through our rulemaking process. So we now can just enforce it as necessary.
All right, thanks, William. Got another question. This is from Joseph Crisologo, and I'm going to give this to Allison. Joseph asked, can you use powder activated carbon to deal with the DBP precursors, and how effective may that be?
That's a good question. So powdered activated carbon can theoretically be used to address various treatment objectives, one of which is DBP precursors, specifically natural organic matter removal. And some systems have had a lot of luck applying PAC for that, and other systems struggle with that. And I really think it's going to be system specific, function of their water quality, their raw water quality, but also how their treatment plan is set up, what kind of dose of powdered activated carbon they're set up to effectively dose and maintain and keep that suspended and not cause other treatment problems downstream, whether they have to add other chemicals when they're adding PAC that can decrease the effectiveness of PAC, and then the type of carbon used. That was discussed, I think, by Kentucky during our second webinar. That can have an impact as well. So it's doable, but it's something that definitely needs to be evaluated for each water system if they want to head down that path and determine whether it's a cost-effective approach or maybe there are better ways for them to try to remove precursors.
All right, thanks, Allison. We've got another question from Joseph. I can cover this one. He asked, it seems as if tank cleans can help resolve some water quality problems in tanks, and how often should you clean tanks and what methodology is used? So the US EPA doesn't really have any requirements or guidance on tank cleaning. It's more left up to the primacy agencies. But I did pull some information, and it looks like just in general, it's recommended that water systems clean their tanks ranging anywhere from 2 to 5 years, depending on the primacy agency. And then what methodology is used for cleaning? Basically, it consists of two things. First is just removing sediment within the tank, physically doing that. And then the second part of that is just disinfection. to clean the tank, disinfect it thoroughly after it's been cleaned. And I believe I looked up, there's AWWA standard D101.53. I believe that's the correct standard that talks about disinfecting tanks. I think that's correct. If there's any questions about that, feel free to follow up with me afterwards, and I'll clarify. So I think we got time for just another question or two. We got a question, and it goes to both William and Jackie. I'll let you both answer this separately. Someone wants to know, have you ever encountered any laboratory issues where any data has been brought into question through some of your work that you did with DBP optimization?
Well, that's an interesting question. We see a lot of variation in results. Whenever we do our monitoring, we send all of our samples to our state lab so that we've got consistency with the results that we're getting. But we do see a lot of variation. I don't know if you would consider that an issue, but we do see variation, and we do see systems that labs shop for that reason. William?
Same as Jackie, we see variation. We used to have lab shopping going on quite often. That's actually settled down in our state currently. But we did have, one system that actually got referred over to our laboratory inspectors to actually go look at them. And I believe the laboratory actually got put on provisional basis, but then they were able to correct the deficiencies. And so none of the data was, invalidated, so it still was valid. It's just this laboratory had to, take some corrective actions to clean up some of the stuff they were doing.
All right, thank you both for those responses. We got time just for one last question, and this is kind of a good way to wrap up the Q&A session here. Someone asked, it seems like it'd be helpful for water systems to view these webinars. They asked, may we refer them to these recordings? Yes, please. Please share the webinar recordings with anyone you think that would be of benefit of watching them. Our intent is just to try to get this information out there to anyone that finds it useful. So with that, I would like to thank everyone, again, all the presenters and then all the participants just for watching this webinar series. We hope it was helpful. And just a reminder, the webinar recordings for this recording and all the other ones will be available on ASWA's website. So thank you and
Bye.
Bye.